Welcome to hypothesis testing. Today we are going to talk a little bit in broad terms about hypothesis testing and inference, p-values, these things in general terms. And the reason is because we are going to use these ideas of inferential statistics going forward for the rest of this course and probably most of your statistical career. But I will try to tie this down to some examples and bring in some videos to help solidify these ideas so they're not so kind of in the clouds. So in general, there are two main types of research questions that we might wish to address. The first type focuses usually on what are group differences. Do two or more groups differ on at least one or more criteria or characteristics? So we could do things like comparing group means, counts in groups, or proportions. These kinds of questions can be answered by such things as a t-test, ANOVA methods, and chi-squared test. And we're going to learn all of these things this semester. There's also a kind of different flavor to research questions, and these deal with not are there group differences, but is there a significant relationship between a set of variables? And these kinds of questions ask about association, dependence, and we can use calculations of correlation and regression models to answer these questions. And we will touch on this slightly in this class, but mostly these types of relationship questions will be answered more fully with regression models, which is the 7610 class's focus. So again, in 6600, we're going to focus on t-tests, ANOVA, and chi-squared tests, which are mostly asking, are there group differences on different measurements, whereas correlation and regression are looking at if there are relationships between variables. Now, there is definitely overlap, but we're going to kind of set these as two different types of questions. So we're going to start with this video.
It presents Understanding Statistical Inference. Hi, I'm Dr. Nick, and in this video, I'm going to explain what statistical inference is. Statistical analysis has two main focuses: descriptive statistics and inferential statistics.
So we're starting now.
Descriptive statistics summarize data using graphs and summary values such as the mean and interquartile range. Descriptive statistics can help us identify relationships and patterns. Descriptive statistics do not draw conclusions beyond the data we already have. Inferential statistical analysis does allow us to make conclusions beyond the data we have to the population from which it was drawn. A definition of inference is the process of drawing conclusions about population parameters based on a sample taken from the population. The sample is the data we collect from the population. Here are some examples of populations and samples. The population is all the apples in an orchard. A sample is 100 apples we pick from the orchard. The population is all the chocolate bars we produce on a machine. A sample is the 30 bars we choose to melt down and weigh the nuts from. The population is all the voters in New Zealand. A sample is 1,000 people who are asked their opinion in an online survey. In each of these examples, we can use the data from our sample to draw some conclusions about the objects or people in the population. For example, we want to know about the weights of the apples in the orchard, so we take a sample of apples and weigh them, and use that information to draw conclusions about the weights of apples in the whole orchard. There are three main ideas underlying inference. A sample is likely to be a good representation of the population.
That's key.
There is an element of uncertainty as to how well the sample represents the population. And the way the sample is taken matters.
A big time.
First, it is reasonable to expect that a sample of objects from a population will represent the population. If our orchard has only red apples of a fairly consistent size, then we would expect the sample to contain red apples of a fairly consistent size. If our machine is producing chocolate bars with a percentage of nuts within a certain range, then we would expect the sample to also have nuts within that range. If 40% of the people in New Zealand believe that the economy is getting worse, then about 40% of the sample will also believe that. Second, there is an element of uncertainty as to how well the sample represents the population.
Very key idea.
A sample will never be a perfect representation of the population from which it is drawn. This is the reason for sampling error. We have a video about sampling error. Nor will all the samples drawn from the same population be the same. But, through simulation and probability theory, we can get an idea of what the population is likely to be like from the information the sample gives us. For example, let us assume that 40% of the population of New Zealand think the economy is getting worse. If we took a sample of 1,000 people, how likely is it that 50% or more of them will say that they think the economy is getting worse? We can work this out using probability theory, or we can run a simulation on a computer to see what we would expect from a whole lot of samples of size 1,000 taken from a population with 40% thinking the economy is getting worse. This graph is the result of a simulation with 1,000 samples of 1,000 people each, drawn from a population with a proportion of success of 0.4 or 40%. We define success as being that the person thinks the economy is getting worse. It turns out that if the true proportion in the population is 40%, the probability of getting a sample with 50% or more people saying that they think the economy is getting worse is 0. It won't happen. Just about always, the sample proportion will be within about 3% of the population proportion when we use a sample size of 1,000. That 3% is called the margin of error. It can be used to create confidence intervals. Confidence intervals give a range within which we think the population parameter is likely to be. You can see more about confidence intervals in our video, Understanding Confidence Intervals.
So Chapter 6 will do confidence
In Inferential Statistics, we can also test hypotheses. Our videos, Understanding the P-value and Hypothesis Testing, explain these.
which we'll watch.
The third principle is the way the sample is taken matters.
This is often
This
overlooked.
principle relates to non-sampling error, which we also have a video about.
We are gonna.
The sample must be representative of the population, and this happens best when each person or thing in the population has an equal chance of being selected in the sample. In natural or manufacturing processes, we may be able to take random samples reasonably easily. However, when our population consists of people, this can be more difficult and costly, so we do the best we can. We explain this further in our video on sampling methods.
We're not going.
This video has been about sample to population inference. We are interested in what the sample tells us about the population. It is not about causation, which is covered in other videos.
Which we will talk about.
This video was brought to you by Statistics Learning Centre. Visit our website for
Okay, so inference. The main ideas with statistical inference. So we've learned descriptive statistics in chapters 1 through 4. So when we have descriptive statistics, when we calculate those based on a sample, they provide a lot of information, but they rely only on the raw or sample data. They generally describe one variable at a time. They don't address uncertainty or accuracy. They are only as precise as the sample is, and there's no real way to do between and within group differences or associations. So descriptive statistics are very important. I want to stress that making histograms, making box plots, making descriptive statistics by group, those are very important things to do, and those are usually our first step, understanding variables one at a time or two at a time. But descriptive statistics do have a limit, and the limit is that descriptive statistics can really only tell you about the sample that you drew. To know about the population as a whole, we have to take into consideration the uncertainty due to sampling. And to do that, we have to move into inferential statistics. And this includes things like hypothesis testing, which involve p-values, and parameter estimation that involve confidence intervals. So in Chapter 5 here, we're going to focus on hypothesis testing and the p-value. So that's pretty much what we're going to talk about today, hypothesis testing and p-values. Next, Chapter 6, we're going to talk more about parameter estimation and confidence intervals, and we'll bring in the idea soon about effect sizes. So when we're looking at p-values and confidence intervals, both of those ideas are not just saying that our sample represents our population, but that there is some level of uncertainty, that our sample is never going to be an exact replication in it's not mini-me to the population perfectly. There will be some differences from sample to sample. And so we have this sampling error, and that uncertainty we have to build into our hypothesis test. So this leads us to a prime example that we're going to look at, which is smoking and lung cancer.
Local lake, and you notice that the fish you're catching seem to have an unusually high number of physical abnormalities. You learn that a chemical plant recently started dumping waste upstream, and you suspect that this is causing the changes in the fish. Well, what if it's just a coincidence? Everyone's heard the adage, correlation is not causation. So what kind of evidence do you need to support your causal claim?
In medicine, it's common to answer questions like these using randomized controlled trials, in which individuals are randomly divided into two groups. One group is exposed to the potential causal factor, and the other group isn't. Such an experiment could rule out the possibility that some other factor causes the abnormalities, since the only major difference between the two groups is exposure to the potential cause.
We might think that a randomized controlled trial would be too slow, costly, or even ethically wrong. In epidemiology, the study of health-related outcomes in human populations, a different approach is often used, relying on a diversity of evidence.
An epidemiologist might compare fish in the polluted lake with similar fish in another pond. They might also bring in evidence from the lab about the biological mechanism that causes the abnormality. Which strategy, randomized trial or diversity of evidence, should we turn to in difficult cases like this? This question is exactly the one that faced scientists in the 1950s and 60s, trying to determine whether smoking causes death from lung cancer.
In the first half of the 20th century, cigarette smoking became much more popular. During the same period, more and more people were dying from lung cancer. Although the reason for this trend seems obvious today, at the time there was intense debate about the connection between smoking cigarettes and lung cancer. These debates were ultimately concerned with how to move from association to causation. In 1951, two British epidemiologists named Richard Dahl and Bradford Hill began a study comparing British doctors who smoked with doctors who did not smoke or who quit smoking. They found an association between smoking cigarettes and lung cancer deaths, and also that those who smoked more cigarettes had a higher risk of dying from lung cancer.
Not everyone was convinced that these associations proved that smoking causes lung cancer. British statistician and eugenicist Ronald Fisher was quick to point out that correlation is not causation. He wondered whether some other causal factor, like an undiscovered gene that predisposes one to both smoking and lung cancer, explained the association. For Fisher, only a randomized controlled trial yielded entirely unchallengeable conclusions regarding causation. He described a hypothetical experiment in which 1,000 teenagers were randomly forced to smoke 30 cigarettes a day, and 1,000 more randomly banned from smoking cigarettes. He noted that such an experiment could not be done, but argued that in the absence of such an experiment, more research was needed to rule out other hypotheses. Several researchers disputed Fisher's gene hypothesis. Appealing to additional sources of evidence, one group, led by the statistician Jeremy Cornfield, argued that a gene could not spread in the population quickly enough to explain the rapid 20th century rise in lung cancer deaths. Also, a genetic cause could not explain why people who quit smoking had a lower risk of lung cancer death compared to those who continued smoking.
While conceding that nothing short of controlled human experiments could provide a clear-cut and unequivocal victory of the smoking hypothesis, Cornfield and his colleagues concluded that the weight of evidence was enough to support it. In the precedent-setting 1964 Surgeon General's report, a multidisciplinary committee of experts reviewed the diversity of evidence available. they advanced 5 criteria for judging whether the observed association was due to smoking causing lung cancer. Consistency. Across multiple studies, smoking was reliably associated with lung cancer deaths.
Strength of the association. The evidence showed that the risk of death from lung cancer was over 10 times higher among people who smoked cigarettes.
Temporality of the association. Lung cancer developed after people started smoking and not the other way around.
Coherence. The evidence from population studies was supported by other types of evidence, including animal research from the lab.
Specificity. Smoking should only be associated with one disease, lung cancer. This last criterion was violated in the smoking case, but the report recognized that diseases often have multiple causes and that one causal factor might result in multiple diseases.
The 1964 Surgeon General's report was decisive. It concluded that cigarette smoking is a health hazard of sufficient importance in the United States to warrant appropriate remedial action. The next year, Hill expanded the list of 5 considerations put forward by the Surgeon General's Committee to 9, which are now known as Hill's viewpoints. Tension remains between these two approaches to causal inference: diversity of evidence versus the randomized controlled trial. Hill's viewpoints and diversity of evidence are important in epidemiology today, while in medicine, the randomized controlled trial is usually considered the gold standard for assessing the effectiveness of treatments. It's a debate born from the ashes of the smoking lung cancer controversy.
So, Ronald Fisher, it talked about in that video, was one of the fathers of inferential statistics. But as brilliant of a mind as he had for statistics, he had some really crappy ideas, one of them being eugenics, which not tolerating. And another one of his crappy ideas is he really didn't believe that you could document causal relationships unless you did a randomized controlled trial. Now, in a lot of the subjects you are studying, randomized controlled trials are not feasible or not ethical. And so Hill's viewpoints, or this diversity of evidence, is what we usually use in most social science or human subject research in your disciplines. And that includes kind of more than one study to prove something. So I've listed the different Hill's viewpoints on the slide, but the main idea is we have to have replication and lots of different sources to strengthen this association to the point that we can actually say that we have some causal relationship. So one study the truth does not make. The things they talked about in that video, we have to have plausibility. We've got to have some scientific explanation for why this relationship of cause and effect would exist. We need a strength of an association, and that has to do with hypothesis testing in an observational study. Consistency with other sources of research. Temporality is very important. If you have the lung cancer starting before smoking, then it can't have been the cause. So temporality is the sequential ordering of the cause has to come before the effect. Dose response in smoking, people that smoked 2 packs a day should have higher risk of lung cancer or more severe lung cancer than someone who smokes 1 cigarette a day. And so that's what the dose response is that if you have more risk of the outcome with more exposure or the cause happening. Specificity that's the only thing or the primary thing that causes it, and prevention is key. So in the smoking, we saw that once people stop smoking, their risk for lung cancer starts decreasing. So it's something that we can prevent or step into and reduce the direct effect of smoking. And so all of those things are needed when we're doing an observational study to get to the point where we can say we have cause and effect relationships going on. So this is important, not so much when you are running a statistical test, but when you get to the point where you are writing up your conclusions. So after you have your methods section, after you have your results section, when you get to your conclusions, you must be very careful. If you're doing an observational study instead of a randomized controlled trial, which is going to happen a lot, then you need to make sure you couch your results as things are associated. And you can't really, in one study, jump to a cause and effect relationship if you don't have this diversity of information. So hopefully, even if you can't make that claim, your work will be part of making that claim. So causality is a judgment call after a combination of lots of studies. So for statistical inference, the whole idea is that we want to know about a whole population, so we take a sample. And based on that sample, we have a pretty good guess at the population, but we know that different samples will look different from each other and slightly different than the population as a whole. And so we are going to use the z-score or other statistical tests to be able to make a judgment call on the uncertainty, using the uncertainty to measure how likely or unlikely a certain sample is given a certain idea of the population. That's the null hypothesis. So we are going to measure likeliness if we're using a z-score, using a p-value. That's the probability of observing a sample if a population exists in a certain way. So we're not usually going to look at one sample size one or one person. We're going to look at a group of cases or a sample. And we're going to start here in chapter 1 or chapter 5 with sample averages. So sample means. And then we're going to look at one sample, and then we're going to go to two samples and on up. So right now we're looking at one sample, its average, X bar when we're looking at the formulas, and capital M if we're doing APA summarization. And we're going to say the central tendency or the center of the sample, how does it compare? What can we use it to say about the sample average or the sample of the whole population? So we're going to watch another quick video. This one's a little bit shorter about the steps of running a hypothesis test.
Hypothesis testing is a key procedure in inferential statistics. It is based on the idea that we can tell things about a population from a sample taken from it. Hypothesis testing can be explained in 5 steps: hypotheses, significance, sample, p-value, decide. Step 1. Hypotheses. Decide on your hypotheses. You need a null hypothesis, H0, and an alternative hypothesis, H1 or HA. Inferential statistics is based on the premise that you cannot prove something to be true, but you can disprove something by finding an exception. You decide what you're trying to provide evidence for, which is the alternative hypothesis. Then you set up the opposite as the null hypothesis and find evidence to disprove that. It can be said that the alternative hypothesis is usually a thing we are trying to prove or find out about, while the null hypothesis is the opposite or status quo. Note 1. The hypotheses are always about the population parameters, not the sample values or statistics.
Very important.
2. The null hypothesis usually refers to the status quo, the thing we are trying to find evidence against. It generally represents no effect. And 3. The null hypothesis should include a statement of equality, and the alternative should not. Step 2. Significance. Decide on the level of significance. Unless there is a good reason not to, people generally use 0.05 as a significance level, also known as the alpha value. The significance level is the probability that you will say that the null hypothesis is wrong when really it is correct. This is known as a type 1 error.
Horrible name.
Step 3. Take a sample from the population to provide the statistics you need. Step 4. Calculate the p-value. This is almost always done by a computer package. Step 5. Use the p-value to decide whether to reject the null hypothesis. If the p-value is less than the significance level you chose earlier, you will reject the null hypothesis. The sample has given you evidence that the null hypothesis is wrong. We will now go through this step by step with an example.
I love examples.
Helen sells choconutties. Her brother Luke is taking a marketing class and tells her that people will buy more choconutties from her if she gives away a free gift with each packet. Helen is sceptical, so decides to gather data to see if it's true. She decides that for the next month she will try out some days where she offers a free sticker with each packet of choconutties and some when she doesn't. From the month of trials, she will have a sample that can be used to draw conclusions about days in the future. The population in this instance is all days of selling choconutties. The sample is the days that occur in the next month. This is not a random sample, but it is all we can do in this instance. To make the assignment of sticker or no sticker random, Helen will toss a coin each morning, and if it is heads, she will offer a free sticker. She will keep track of her sales for each day. She asks you to help her do the analysis. The first step is to decide on the hypotheses. There are two different circumstances, sometimes known as treatments, offering a sticker and not offering. The null hypothesis is that there is no difference in the sales for the two treatments. The statistic of interest is the mean or average value of daily sales. The null hypothesis can be written H0, there is no difference in mean sales for the population for the two treatments. The alternative hypothesis is written H1, there is a difference in mean sales for the population for the two treatments.
Now this has two
Helen thinks the sales could go up or down as a result of offering a free sticker.
or two treatments.
Written in mathematical terminology, we use mu, a Greek letter to represent the population mean.
Now I'm going to stop this video here because this example is doing two means. And in chapter 5, we're only going to do one mean. We will move into two means, but not in chapter 5. So I'm going to stop this and move on to the next video, more about
I'm going to briefly go over the essentials of hypothesis testing. And in the second part, I will test a claim about a population mean. A hypothesis is simply a claim or statement about a population parameter such as population mean, variance, proportion, and so on. In inferential statistics, we study a sample or samples and use the results to generalize on an entire population or populations. Suppose we make a claim that the average age of all college students in a city is 23, which we write as mu equals 23. Since this hypothesis contains equality, we refer to it as the null hypothesis, represented by H0. The complement or opposite of the null hypothesis is the alternative hypothesis, represented by HA or H1. In this case, the alternative would be that the mean is not equal to 23.
Now I want to point this out. When you write your hypotheses, the hypotheses are always about the population parameter, so the mean would be mu, not x bar, and the null hypothesis always has always has an equal sign, or if it's a less than or greater than, it also has to have the equal bar underneath it. So the null hypothesis is always population parameters, so for mean it means mu, and it always has inequality as part of it.
Use this hypothesis for two-tailed tests because the alternative basically means that the mean could be less or greater than 23. Suppose instead we want to test if the mean is less than 23. Since this statement does not contain equality, we will assign it to the alternative hypothesis. And the null will be the opposite, that is, the mean is greater or equal to 23. And if we're testing if the mean is greater than 23, that will be the alternative hypothesis, and the null will be mean less or equal to 23. These two are hypotheses for one-tailed tests. This is for a left-tailed test because the alternative hypothesis has a less than sign, and this is for a right-tailed test because the alternate has a greater than sign. Note that the alternative hypothesis determines the tail of the test. Note also that the alternative hypothesis never contains equality, and the null always contains equality. In fact, some only use equal sign for the null hypothesis. Now, when we conduct hypothesis tests, we are primarily trying to decide whether or not to reject the null hypothesis. If we reject the null hypothesis, we will say we have enough evidence to support the alternative, or to say that the alternative is true. If we don't reject the null hypothesis, we will say we don't have enough evidence to support the alternative. We usually don't say that the alternative is not true. We only say that we don't have enough evidence to support it. Now, to determine when to reject the null hypothesis, we select a significance level alpha. 5% or 0.05 is the most commonly used alpha value. 0.10 and 0.01 are also often used. The significance level helps specify the size of the region where the null hypothesis should be rejected. We call that region the critical or rejection region. For a two-tailed test, alpha is divided by 2 into both tails. So we reject the null hypothesis in the tails and we don't reject it in the middle here. For one-tailed tests, alpha is not divided. So for the left tail test, the rejection region is in the left tail. and it's in the right tail for the right-tailed test. Once the rejection region is set, we then calculate the test statistic. If the test statistic falls in the rejection region, we reject the null hypothesis. Otherwise, we fail to reject it. In the second part of this video, we will look at this example to illustrate the hypothesis testing process. Thanks for watching.
Okay, and we're going to do a similar example in ours. So let's go over the 5 steps of a hypothesis test. And these 5 are going to be the same whether we're doing a z-test, a t-test, a chi-squared test, an f-test, and a ANOVA test. All statistical tests have these 5 steps. And these mirror the scientific method. Number 1, we, based on our observations, create some hypothesis. Now, with a hypothesis test, we actually do dual hypotheses. The null is always that basically nothing's going on. There's no effect. It's the status quo. That's the straw man we're trying to knock down. Null hypothesis. Alternative hypothesis is usually the thing we wish we could prove or we think we are going to prove. So null and alternative, they are 2 sides of the same coin. Next, we select the significance test at alpha level, and if we're going to do 1 or 2 tails. Now, if you're doing homework in our class and it doesn't say anything about alpha, the default we're going to go with is alpha equals 0.05. And if it doesn't say anything about the number of tails, we're going to default to doing 2 tails. And we'll talk about why, but I just wanted to put this out there. If you have nothing else to go on, alpha 0.05, 2 tails. So you have your null hypothesis and your alternative hypothesis set. You think this is going on. You set up your alpha level and your number of tails. So now we have set our rejection region based on that. Then you go collect your sample and get your data. Then based on the data, you calculate your test statistic, and putting those things together, you decide whether or not you have enough evidence from your sample under these conditions to reject the null hypothesis or fail to reject. So the way we're going to make that decide that conclusion is based on a p-value. Now, the definition of a p-value is very wordy. The languaging of statistics is very awkward. English doesn't capture statistics very well. Every word in this definition is required to make it fully accurate. So the definition of a p-value is the probability of observing a test statistic or a sample as extreme or more extreme if that null hypothesis is true. So the p-value is always based on the null hypothesis. That's very important. So here, let's watch another little crash course statistic video. This one's a little bit longer.
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. We've been talking a lot about how to tell whether 2 groups are different, like whether there's more car accidents on rainy days than snowy days, or whether the IQ of university students is actually different from the population. Today, we're going to start a conversation about statistical inference, which tells us how we can go from describing data we already have to making inferences about data we don't have. If you've watched any of the other videos in this series, you've heard a lot about uncertainty. It comes up endlessly in statistics, and uncertainty is at the core of what inferential statistics is all about, making decisions about ideas or hypotheses. I might be interested in whether listening to Mozart while doing calculus homework improves my calculus grades, but I need to test my hypothesis. I can't just have an idea and claim it's correct without any evidence. One thing we need for sure is data, so we could randomly sample 2 groups of 25 people and make half of them listen to Mozart and half do their homework in silence. We collect their calculus grades and see that those who listened to Mozart scored on average 3 points higher than those who didn't. So Mozart's good. Problem solved. Breakout sonatas, right? Unfortunately, no. We've seen that sample parameters like the mean are just estimates of the mean of the population that they're taken from. The sample mean score of the Mozart group is higher, but we don't have sufficient evidence that the population mean of Mozart listeners is higher than those who did their work in silence. We may have gotten an especially high sample mean that isn't close to the true population mean. So we need a way to test our hypothesis while taking into account the random variation of sample means. In theory, one way you could test a hypothesis hypothesis or model is by how well it predicts the data you got. For example, you and your best friend really love giraffes, and you spend a lot of time watching them at the zoo and drawing sketches of them. So you both have a hypothesis about the average number of spots a baby giraffe has, but they're slightly different. You think that baby giraffes have an average of 175 spots with a standard deviation of 50 spots, and your best friend thinks that baby giraffes have an average of 209 spots with a standard deviation of 45 spots. With the permission of your local zoo, of course, you begin to collect a random sample of baby giraffes and count how many spots they had. Your sample of 25 baby giraffes had a mean of 200 spots. Now that you have the data, you can use it to evaluate which one of you is more likely to be right. Both you and your friend have a model or idea about what the population distribution of baby giraffe spots is. If you're right, then the sampling distribution of all the possible sample means we could get looks like this, and the distribution of sample means for your friend's model looks like this. Let's look at where our sample mean of 200 lies on both of these distributions. You can see that we're more likely to get a mean of 200 spots under your friend's hypothesis than yours. If your model were correct, a mean of 200 spots is pretty rare. It's in the top 1.2% most extreme values we'd expect to see. Whereas in your friend's model, a mean of 200 spots is only in the top 32%, which means it's pretty common that we'd see sample means around 200 if your friend's model was correct. But we don't always have predictions that are as specific as you and your friend's predictions about baby giraffe spots. We might have a more general hypothesis, like that the average number of baby giraffe spots is more than 200. But that's all you really know. In situations like these, one common method of testing is null hypothesis significance testing. You have a hypothesis that people with a certain gene, we'll call it gene X, eat a different amount of calories than the general population. Null hypothesis significance testing asks you to test a different hypothesis, which says there's no difference or effect of this gene. And we'll see how well this null hypothesis predicts the data we've collected. In this case, the null hypothesis, or null model, is that the population mean caloric intake for people with gene X is actually 2,300, the same as the regular population. If the null hypothesis is found to be infeasible, we can reject it. We can represent this hypothesis like this. This might seem like a pretty roundabout way to test your theory that people with gene X eat differently, and that's because it is. Null hypothesis significance testing is a form of the reductio ad absurdum argument, which tries to discredit an idea by assuming the idea is true, and then showing that if you make that assumption, something contradictory happens. For example, you can use reductio ad absurdum to show that there's no largest positive integer. Let's assume there is a largest positive integer. We'll call it AB for absurdly big. Now we add 1 to AB. That would be a larger positive integer, which would be absurd since AB is the largest. Therefore, by reductio ad absurdum, there is no largest positive integer. By the way, if this kind of argument sounds familiar, it might be because reductio ad absurdum is like proof by contradiction. Let's test the null hypothesis for our gene X case. First, we assume that the mean number of calories eaten by people with gene X is 2,300, just like the regular population. If we can show that this assumption makes something absurd happen, then we can reject the idea that it's true. With data from 60 people with gene X, we see that the mean number of calories eaten was 2,400, with a sample standard deviation of 500 calories. We have to ask how rare or absurd it would be to get a sample mean that is this far away from our assumed mean of 2,300. Essentially, we imagine that we take a random sample of 60 people with gene X over and over and over again and calculate the mean. Then we ask how many times out of all those experiments do we get a sample mean that's as far away from 2,300 as our actual sample mean of 2,400 is. Even if you haven't heard of the term null hypothesis significance testing, you might have heard of p-values, which have been covered everywhere from academic journals to BuzzFeed articles. A p-value answers the question of how rare your data is by telling you the probability of getting data that's as extreme as the data you observed if the null hypothesis was true. If your p-value were 0.10, you could say that your sample is in the top 10% most extreme samples we'd expect to see based on the distribution of sample means. If we assume that the null hypothesis is true, and the mean caloric intake of people with gene X is 2,300 with a standard deviation of 500 calories, the distribution of sample means will look like this, and tells us which means we expect to see and how often we expect to see each of them. Sample means around 2,300 are most common, but we'll also often see sample means a little bit further away. We can use this distribution to calculate our p-value. This is similar to how we compared the likelihood of 200 giraffe spots in you and your friends' models, but with only one model this time. Here's our sample mean of 2,400 on this graph. Only about 8.99% of the possible sample means are higher than 2,400. So it's not that unlikely that we get a sample mean that's this high if the true population mean was 2,300 calories. This is called a one-sided p-value, since it only tells us the probability of getting a sample mean that's higher than 2,400. Often when we ask scientific questions, like does this medicine have a different level of efficacy than the existing treatment, we don't know which direction the effect will be in. The new medicine might be better, or it might be worse. Gene Xers might eat more, or they might eat less. Because of this, and a few other reasons we'll talk about later in the series, p-values are often two-sided, meaning that we look at how far away a value is from the mean, regardless of if it's higher or lower. This allows us to reject the null hypothesis if our value is significantly higher than the mean, or if the value is significantly lower than the mean. Because the distribution of sample means is symmetrical, if 9% of the samples of caloric intake are higher than a mean of 2,400, about 18% of sample means for calories would be as far away or further from the population mean than 2,400 is in either direction. In other words, a two-sided p-value is a measure of how extreme your sample mean is, because it tells you how often you'll get a value that's as or more extreme than the one you got. The smaller your p-value is, the more rare it would be to get your sample just by random chance alone, if the null is true. In our example, we learned that if we assume that there's no effect of gene X on caloric intake, then there would be an 18% chance, about 1 in 5, that we'd see a sample like this just because of the random variation of samples. To finish our attempt at reductio ad absurdum, we have to decide whether this sample is absurd or extreme enough to lead us to believe that the sample probably isn't from the null distribution. But that decision isn't always an easy one to make. It's not clear how rare or absurd a sample needs to be before I decide to reject the idea that the sample was taken from a population that has the null distribution, especially since we don't have another distribution to compare it to, like we did with the giraffes. Our p-value of 0.18 tells us that if we took a sample like this over and over and over, about 1 out of every 5 times, we get a sample with a mean caloric intake that's further from the mean than 2,400 calories is. 1 in 5 is not bad, but a 1 in 20 chance might be better, and a 1 in 100 chance better than that. Some statisticians see a p-value as a continuous measure of evidence. A p-value of 0.18, like ours, might be considered pretty weak evidence that our sample isn't taken from the null distribution, but it's better than a 0.19, which is in turn better than a 0.20, and on and on. However, in null hypothesis significance testing, p-values need a cutoff. We could set a cutoff at 0.05 and say that a p-value that is less than 0.05 is sufficient evidence to allow us to reject the idea that the null hypothesis is true. When we can reject the null hypothesis, we consider our results to be statistically significant, which is basically a phrase that just means unlikely due to random chance alone. As we'll see later on, it doesn't always mean that it should be significant or meaningful to you. A cutoff of 0.05 means that we want our sample value to be at least in the top 5% of most extreme values in our distribution before we consider the value evidence against that hypothesis. And any p-value less than the 0.05 cutoff counts. 0.049 leads to the same conclusion as 0.0001. Both cause you to reject the null hypothesis. The current scientific consensus in most fields is that your cutoff, or alpha, should be 0.05, but there's huge disagreement in the field of statistics about whether 0.05 is appropriate, and we're going to dive into that later. In the meantime, I'm going to go get 24 more giraffes so I can compare my model with my friends. Thanks for watching. We'll see you next time.
Okay. So, to recap, she talks so fast. The very first thing we need to do in a hypothesis test is set up our hypotheses. So the null hypothesis It's always going to have some things. It's always going to be for the population parameter. So it's always going to have mu instead of x bar. If we have one sample, we're going to have one mu. If we have two samples, we'll have two mu's. And so we'll have to tell the difference, we can put mu with a little 1 and mu with a little 2. But it's always going to have some part of the equalness in it. The alternative hypothesis never has equal in it. So we can use the not equals or a less than or a greater than. Okay, now let's learn a little bit more about p-values. This is a shorter video.
And I'm on a mission to equip you with the information you need to thrive in our data-rich world. If you've ever seen a news story about a scientific study, you've probably heard something like statistically significant results. More likely than not, what this is referring to is a scientific study that found something like p is less than 0.05. In this video, I'm going to do two things. First, I'm going to explain what it means when someone says something like statistically significant result. Then I'll give you an intuitive explanation of what those p-values are, and finally, if you stick around to the end of this video, I'm going to explain why we use a threshold of 0.05 and not say 0.04 or 0.08 or 0.15 or anything else when determining statistical significance. So let's start with what statistical significance is. In the scientific world, a key idea is that we can never prove something to be true. That seems like a pretty strange thing to say, since it sure seems like all that science is concerned with is proving things. The Earth is round, the sky is blue, gravity attracts objects together. It sure seems like those are all proven to be true, and yet they're actually not. Instead, what science does is provide evidence that something isn't true. This is a pretty subtle distinction, but it's basically the whole point of statistical significance testing, so let's unpack it. Most likely, you believe that if I drop this ball, it will fall to the ground. I bet you're willing to go a step further and say that, assuming I don't do anything to trick you, this is always going to be true. In other words, no matter what, when I drop this ball, it'll fall to the ground. The problem, though, is that we can't ever test that last idea, that this will always happen. Always is a pretty long time, and to show that something always happens, you need to observe an outcome in every single possible condition that could exist across all of time. You really can't prove to me that 100 years from now this ball will still fall down when I drop it. I mean, it probably will, but you can't prove it. Instead, let's see what you can do. You can think about the opposite case and make the prediction that if I drop this ball, it will not fall to the ground. So when I do drop it and it falls, we just provided evidence against the idea that a drop ball always stays in place. And we can repeat this a bunch of times if we want to provide even more evidence against the idea that the dropped balls always stay in place. No surprise, the ball keeps dropping, and the evidence against the idea that a drop ball always stays in place keeps mounting. At some point, we feel pretty confident saying that we reject the idea that a drop ball always stays in place. Note that we didn't prove that a drop ball always falls to the ground. That we can't do. Instead, we can disprove the idea that a drop ball always stays in place, which sure seems like me saying that a drop ball always falls down, but that's not the case. We don't have evidence to prove that drop balls always fall down. We've only observed that a few times, and who knows what will change in the future. So what does this have to do with statistical significance? Well, before we get into that, if you like what you're seeing, please take a moment to like this video, subscribe to this channel, and click that little bell icon so that you don't miss out on any new content that I put out.
Actually, it's pretty good.
With that said, let's figure out what this all has to do with statistical significance. When I say that something is statistically significant, I'm comparing the result of some kind of analysis to what is called a null hypothesis. A good analogy to help understand what a null hypothesis is a jury looking to convict a defendant or not. Our legal system uses the idea of innocent until proven guilty. With statistics, that innocence is the null hypothesis. It's the idea we assume to be true until evidence is presented to show us that it's not. For a jury, that evidence might be DNA at the scene of a crime or eyewitness testimony. With enough evidence, the jury rejects the idea of innocence. For statistics, think of our ball dropping example. If you know nothing about how the world works and make a prediction that dropped balls never fall, that would be your null hypothesis. And when you see that the ball really does drop, that would be the evidence you use to reject that null hypothesis and conclude that drop balls don't always stay in place. If we're testing if a drug is effective at reducing heart disease, our null hypothesis is that the drug is not effective. If after conducting a randomized experiment, something I talk about in detail in a different video that I'll link to below, we find that the drug reduces heart disease by some meaningful amount, we can reject the null hypothesis that the drug is not effective. Note that we haven't proven that the drug is effective because we haven't tested it in every single conceivable case, just in our single experiment. Instead, we've provided evidence to reject the null hypothesis that the drug is not effective. The more experiments we run that show that the drug is effective at reducing heart disease, the more our confidence grows. We can never get to the point where we are certain that the drug reduces heart disease, but we can get close enough where practically we can start prescribing the drug. So when you see something reporting a statistically significant result, what they really mean is that there was enough evidence provided to reject a null hypothesis. But how much evidence do you need to do that? That's where that p is less than 0.05 comes in. I'm not going to get deep into the statistical distributions of all this. Instead, I'm going to provide the intuition for what p is less than 0.05 means. First, 0.05 is a cutoff. It's something we compare a statistical result to determine if we have what is typically called a statistically significant result. Without getting into the weeds on different statistical tests, whenever you conduct one, there is a corresponding p-value. The smaller the p-value, the greater confidence you have in rejecting whatever the null hypothesis is. So let's say we are comparing the efficacy of that heart disease drug from before to a control group that didn't get the drug, and we found that fewer people suffered from heart disease after taking the drug compared to those who didn't take it. We might find a relatively small difference between these two groups and get a p-value for that comparison of 0.60, which is well above our cutoff of 0.05. That would mean that the difference in heart disease across our two groups was so small that we don't have enough confidence to reject the null hypothesis that the drug doesn't work. In another case, we might see a large difference in heart disease across the two groups and get a p-value of, say, 0.01, which is less than 0.05, so we say that we do have enough evidence to reject the null hypothesis that the drug doesn't work. In that case, we start to build confidence that the drug is effective. Getting a bit more precise though, that p-value has a very specific meaning. Let's take the case from before of a p-value of 0.01. This means that if the null hypothesis were true, if the drug really doesn't work at all, the chances of us getting the result that we did, or one even stronger, is only 1%. In other words, given what we observed, the much more likely case is that the null hypothesis is actually false. It would be incredibly unusual for us to find this result if the drug really didn't work at all. On the other hand, if our p-value from that drug trial was that higher value of 0.60, that means that if our null hypothesis were true, the chance of us getting the result that we did is a whopping 60%. In other words, it's very likely that the null hypothesis is, in fact, true, because we'd expect to see this result 60% of the time, even when the drug does nothing at all. So as p-values get smaller, we increase our confidence in rejecting the null hypothesis. Bringing back that p is less than 0.05 idea, basically that says that the convention that many scientific disciplines follow is that to have enough evidence to reject a null hypothesis, your result needs to be no more than 5% unlikely if the null hypothesis is actually true. Any more than that, and we say we don't have enough evidence to reject a null hypothesis. And any less than that, and we say we do. Which brings us to the final point. Why 0.05? As in, why is the cutoff for whether something is statistically significant or not 0.05? Why not 0.20 or 0.01? The answer is actually simple. It's totally arbitrary. Someone at some point in history, probably a man named Ronald Fisher back in the early 20th century, decided that 5% was the value. And we've stuck with it ever since. There's really no good reason for 5% to be the cutoff for statistical significance. It's just a convention. If you want to be sure that your evidence is very strong in its ability to reject a null hypothesis, pick a smaller cutoff like 0.01. If you don't care as much about strong evidence, pick a higher value like 0.15. It actually doesn't matter. There's no right answer. 0.05 as a cutoff is just a convention we all agree to use, but it doesn't make it right. In fact, there are plenty of people who argue that we should throw away this whole idea of statistical significance testing, and instead focus on things like confidence intervals, Bayesian estimates, and effect sizes. In some ways, those people are right. On the other hand, conventions help us have a common language about things like evidence. When we have a shared language about science, we can communicate better, and that allows knowledge to grow. To be fair, I glossed over a lot here, like how to calculate those p-values, how to deal with different distributions, and how p-values are related to, but not quite the same thing as false positive rates. I did this so we can stick to the heart of the intuition you need to understand what significance testing is. But if those are topics you find interesting and want to learn,
you can watch his other videos or come back to our class. So I want to go back to the analogy that was brought up about the court system, the legal system here in the United States. So in the United States, if you are charged with a crime or someone tries to sue you, the prevailing theory is you are innocent until proven guilty. And this is how in inference we assume the null hypothesis is true until we have evidence against it. And in the jury, how much evidence do we need? Sometimes a trial or a jury will say that there's inconclusive evidence. Sometimes we use the phrase beyond a shadow of a doubt. In statistical testing, the common, like you said, convention is the arbitrary level of alpha equals 0.05. We're going to talk about that a lot more in just a minute. But I want to go back to this. At a jury trial, when charges are placed forth, always we start off under the assumption that we have an innocent party, and it's up to the prosecutors to bring forth evidence to disprove or knock down, or to provide enough evidence, not insufficient evidence. You can't just have a little evidence, you got to have strong evidence against the innocence. So, our assumption for hypothesis testing for inference is that we always work forward based on the assumption the null hypothesis is true. So we always assume innocence, that there's no effect, a drug's not effective. We always start that way, that there's no relationship between a therapy and an outcome. There's no evidence. We always start that there's no difference between prior teaching methods and this new teaching method. Always start off null hypothesis and no, nothing's going on, there's no group differences, there's no association. Then when we gather our data, we see if that data provides evidence against that null hypothesis by the p-value. And the p-value tells us the chance of getting data that extreme or more extreme if the null hypothesis is true. And if that is a small chance, then we have data that's absurd under the null hypothesis, the innocence assumption. And therefore, evidence against the null hypothesis would lead us to reject the null hypothesis in favor of the alternative hypothesis. So usually we use this cutoff criteria of alpha equals 0.05. But as the video said, that is kind of arbitrary. It is good to have a common language and a common benchmark, but there's not just one. And you can argue, and people do all the time, about what alpha should be. And it depends on the situation. So, key here, the last thing that's on the slide, we never accept the alternative hypothesis. In fact, we never accept any hypothesis. We always are just looking at evidence, and the evidence either enough evidence to disprove the null or not enough evidence to disprove the null. We never accept anything. So big difference in the language we use. So we saw that sometimes we have one and sometimes we have two-tailed tests. A two-tailed test has an alternative which uses the equal with a slash through it, the not equal to. That two-tailed hypothesis shows up in our picture of our normal curve with two tails, two beyond z areas shaded that together are equal to the alpha level. So if we have alpha of 5%, then 2.5% go in each tail, or 0.025. If we have a one-tailed test, that suggests that our results are only going to be seen in one direction, and therefore all of the alpha, in this typical case 5%, is placed or found in one of the tails. And this could be one or the other, but you have to determine it beforehand. There's no computational difference here. It's just when we look up our z-table, whether we're putting 5% in one tail or 2.5% in each of the tails, depends on if we're going to set up our hypothesis to begin with as a one-tail or a two-tail test. So when should we use a one-tail test? When should we use two? Well, there are some circumstances that warrant a one-tail test. Often this is used if we're doing a replication study where there is already evidence that it's clearly going to be in a certain direction, and we just are trying to replicate or show that, yes, that is the case. However, it is vastly preferred in almost every discipline, in every niche that I've seen, to run two-tail tests whenever possible. And that's because the two-tailed test is more conservative. It allows for the outcome to be in either direction. And so it looks suspicious if you try to publish results that are a one-tailed test. So I would say, by and large, plan on always running a two-tailed test unless you have a very good reason not to. And I would definitely talk to colleagues and mentors before you ever go that direction. So on homework and tests for our class, if it doesn't say otherwise, always go with two-tailed test and alpha 0.05. If I want you to do a one-tailed test, I will tell you so, because those are a rare situation. So going back to the court case scenario, I've set up this table a little bit different than the one in the book, but on the left-hand side, I have the truth. So there is some truth. So in a court case, the person that's on trial is either innocent or guilty. There is some truth. We usually don't know that truth for sure, like no. But there is some truth out there. Either they robbed the bank or they didn't. And so the same goes in statistical research, that either this method of teaching second graders to read is truly better or it's not better. In fact, maybe it's even worse. We don't know as a researcher, but there is some truth out there. So the two rows here are, in fact, the real truth that we don't know, that we want to know, whether or not so the innocent here would be the null hypothesis, nothing going on, nothing to see, and the guilty truth would be the alternative hypothesis. So we always assume innocence until proven guilty in our court of law. We always assume the null hypothesis in inference until we have enough evidence to prove otherwise. And so after we run our statistical test, after the court battle goes forth, we have to have a verdict. And the verdict, other than the hung trial, we have either we are going to convict or we're going to fail to convict. So there are two ways that we can get the correct verdict. If the party that's being charged with the crime didn't do it, if they're truly innocent, we can get that right by failing to convict them. That's a correct decision. However, there's another way to make a correct decision. If that party is guilty and we convict them, that is a correct pairing. So there are two ways to get a correct result out of a jury trial. Same way in inference, there's two ways to go about a hypothesis test to get a correct conclusion. So if the null is true, the null hypothesis is true, there is nothing going on, and we say at the end of our conclusion there's nothing going on, that's correct. But if something is going on, there is a group difference or there is an association, and we say that there is, that's also correct. So it's hard to distinguish beforehand or even after if you're correct or not, but there are two different ways I want to show you that you could be correct. And just like there are two ways to be correct, there are two ways that you could get your result wrong. And whoever came up with this, very poor naming. They call them type 1 and type 2 errors, and I hate the naming. They're terrible. Type 1 error is like, and the way I remember them, is the little boy who cried wolf. So the little boy was set out to guard the sheep, and he got bored because nothing was going on. And so he said, I know how we can have fun. And so he runs into town and says, there's a wolf. So all of the people in the town grab their pitchforks, grab their torches. Everybody races out to defend the sheep, to save them from the wolf. And everybody runs out and the sheep are just grazing. And the little boy laughs and said, I fooled you. And everyone got mad and said, don't do that. We wanted to, we're glad the sheep are okay, but you've just, taken us away from our work. That's a type 1 error, when nothing is going on, but someone says there is. So this is when you say that there's evidence against the null, but there really isn't in truth. So the little boy did this. He made his first type of mistake, this false positive alert, multiple times. And eventually, the townspeople learned to not believe him. Then, in the future, one day comes that a wolf actually does show up and start eating the sheep. And so the little boy runs into town and he screams, there's a wolf, and everyone ignores him. So this is a case of a type 2 error, when there is something going on, but the town people said, no, there's not. So a type 2 error would be if we have someone guilty that has failed to be convicted. So in inference, it would be when there is an association, but we fail to say that there's an association. When there is a group difference and we say that there is none. So just like there are two ways to be correct, there's two ways to have an error. So there's those 4 different outcomes to a test. Again, that's only if you know the truth. In reality, we don't know the truth, especially when we're studying something new. So choosing your alpha level is involved with these two kinds of errors that you can make. The type 1 error is a false positive, And a type 2 error is a false negative. Denoted in these pictures, type 1 is a false alarm, so telling a man that they're pregnant. They're saying there's something going on when there really isn't, versus a type 2 error telling this obviously ready to give birth woman that, nope, not pregnant. So that's failure to say that something that's going on really is. So these two kinds of errors are tied up, and not exactly the same as, but related to alpha. So alpha is the long run type 1 error, and power is the reverse. We're not going to talk about this in detail right now. We will in a future chapter. But some people say, well, if alpha is the chance of making a type 1 error rate long term, then why don't we make it smaller than 0.05? 5% false positive rate, that's small, but wouldn't it be better to make it 0.01 or 0.001? Yes, but there is, I want to bring up, when we choose to make alpha more small, we inadvertently affect the type 2 error rate and we lose some power. So there is some legitimate reason why we wouldn't want to choose alpha to be smaller than 0.05. Okay, so this is about the end of today's video, and I wanted to just wrap up with the assumptions of a one-sample z-test, since that's what we're focusing on chapter 1. So there are 3 assumptions. Every time we learn a test or a model or an inferential test, there's always assumptions on which it's based. And if you don't meet the assumptions, the test is likely to be inaccurate. It's untrustworthy. So here are the assumptions for a one-sample z-test. Number 1, your sample needs to be drawn at random. And this goes back to one of our first videos, that the sample is representative. Now, there are reasons why we can't do a fully randomized sample, simple random sample where you draw names out of a hat, but we want to do everything in our power as a researcher to ensure that our sample is as random as possible so that it ensures that it's representative. We don't want to make it random just to make it hard on ourselves. We want our sample to be representative. And there's no way that you can statistically test if a sample is representative, and there is no way to fix a non-representative sample. And so I just really want to point that out. If your sample is garbage, it's not representative, there is nothing any statistician or any statistical program can do to fix it. Nothing. It's garbage. Garbage in, garbage out. The second assumption is that the standard deviation of the sample population that you actually sampled from is the standard deviation of our comparison population. And again, this is something that we usually have to assume there's no statistical test for. But the third assumption is testable. So the third assumption is that whatever variable we're measuring has a normal distribution in the whole population. So this last assumption is the only testable of the 3. However, it's probably the least important of the 3 due to the central limit theorem. So if we remember back to chapter 4 and chapter 3, if we take a sample from a population and calculate the mean, the more samples we take, and the bigger the samples, the more the distribution of the mean will resemble the normal distribution. And the sample does not have to be that large for this central limit theorem to take over. But we can test this. Now, there are different tests out there, but the best way to test if a distribution is normal is to actually plot it. And you can make a histogram or a box plot. We've learned how to do those. And this chapter, we're going to learn how to make Q plots. They're about as easy. They take about the same amount of code, but all 3 of those plots will help you visually look at the distribution in a sample to determine if the sample values are roughly normally distributed. You can also use descriptive statistics like skewness and kurtosis, but the guidelines on what's too skewed or what's too much or too little kurtosis are less established. You'll find some people reference and cite some, but really there's not a lot of consensus there. So if you really do need to test if some population is normal, probably the prevailing consensus is that the Shapiro-Wilks is the best test if you want to get a p-value for if you have a normal distribution. And this brings up a whole can of worms, because what should your p-value be to be considered non-normal enough? I mean, really, when I am pushed, I will always go with looking at a histogram over calculating the Shapiro-Wilks test for normality, but I will show you how to do all of those things. We already know histograms and box plots. Today I'm going to show you in our next video QUQ plots and Shapiro-Wilks test and how to interpret those. So that's how we go about testing if the assumption of normality in the population based on our sample data. And I'm putting a link down here at the bottom of the slide if you want to come back and look at some other resources on that. So, yeah, I'm going to leave it here. And I'm going to stop this recording and come back, and I'm going to hit APA results, as well as we're going to do an example by hand of a one sample z-test, look at some conversations about hypothesis testing and how to do the normality tests and plotting of QQ plots in R. So that's it for this video.